10. So today we're going to cover the material for lesson 6, energy transfer in the atmosphere. So this lesson can help you develop your notes for that package, for the notes package, and that in turn can help you with any kind of test I have on the topic, and also with your climate change project that you guys are hopefully working on by now, or maybe I know some of you have possibly done it. So I'm going to go through some of these topics, and I actually decided I'd like to explore climate a little bit more deeply than it's already there in the notes package. One thing I'll just start reminding you of, by the way, because I'll use that term a little bit, weather and climate, that weather is just short-term events like it raining tomorrow or not, or the wind on a particular day of the week, whereas climate is long-term patterns in weather that are based on weather that happens over the course of several years, rather than just a snapshot. So when we're talking about climate, that actually we're starting to have a conversation about what are the general rules for how weather behaves, how the climate acts, how measures of the climate behave on different parts of the world, and looking at some of the rules behind that. So first of all, and I guess I should also back up and say, why are we covering this? We're covering this because, well, this is one aspect of energy transfer that's hugely important in your lives. We're dependent on Earth on, of course, radiation from the sun, but we're also dependent on the climate being a certain range of temperatures, and on what these cycles of energy transfer provide us with, like fresh water. So first of all, I think it's useful to start talking a little bit about where this energy is coming from and what it's doing. So the sun, of course, is the major source of energy that acts on the atmosphere and also in the hydrosphere, the sphere of water. The sun's energy comes in the form of radiation. Radiation is energy that can travel through the empty vacuum of space. Now, when it hits the Earth, though, there is an energy transformation. The radiation energy is being transformed into thermal energy. That is the energy of moving molecules. So that's an energy transfer that becomes really important when we're looking at how the sun affects the climate. Now, one possible outcome of that is that heat can be transferred into the ground, which explains what makes the ground warm on a sunny day. But also, that heat can be transferred into the atmosphere. One way that can happen is that there can be evaporation of water from the surface, and that brings water vapor into the atmosphere. But I guess more broadly, I wanted to say that as radiation hits the molecules in the air, some of those molecules are made to be more excited and to travel faster. This is what can increase the temperature of gases in the atmosphere, is when units of radiation, like think about particles of light, strike molecules and make them excited so they move faster. An outcome of this, them moving faster, is, other than an increase in temperature, is that the space between those molecules in the air increases. They space themselves out a little bit more. This is the principle behind, say, a hot air balloon that you blow up with, a big bag that you basically blow up with hot air, which then rises. What's happening inside the hot air balloon, it's not like a rocket or anything like that. It's simply a giant bubble of air that is at a lower density than the air in the surrounding atmosphere. As a result, it floats. It goes upwards towards parts of the atmosphere that are at a similar density, whereas the air around the hot air balloon, we can think of it as that air sinking to the extent that the balloon is rising. So what we're talking about there is happening. That's a process called convection. Convection is most active where the sun's rays strike the Earth's surface at a high density of sunlight, of energy striking that surface. What I'm going to show you now is Well, I'm going to start with this concept of a Hadley cell, because I want you to think with this diagram right here, where is the sun striking the Earth's surface at the highest angle? Okay, what does that mean? If the sun, let's say the sun is coming from the right of the screen, over here. Okay, sunlight coming from over here that strikes right here is striking at a very low angle, a very shallow angle. A unit of sunlight that strikes the Earth in this little spot right here is spread over a much larger area than the same amount of sunlight that hits the Earth here. This is something that, well, I'll simply say that this explains why it's so much hotter in the tropics than it is in the Arctic and in the Antarctic, because the sun's rays in the tropics, as they strike the Earth's surface, are not spread out over such a large area as they are further north or south of the equator. Now, an outcome of that, we see it right here. This involves convection and the sun's energy and the specific location of where the most sun's energy is hitting the Earth at any one time. In general, at the tropics, we have the highest amount of sun's energy per unit area striking the Earth. Here's the outcome of that. At those places around the equator, it gets very hot. Where there is surface water, that surface water evaporates. There might be a lot of surface water that's available, so you can get very humid climates as a result. The bottom line is, if you've ever been to the tropics, you know how muggy it can be there because there's such high humidity in the air. Now, with all that heat coming from the sun, this causes convection. Moisture has been picked up because of the energy being provided by the sun. That warm, moist air then rises. It rises then, and it moves. Having done that, it doesn't just go all the way off into space. Eventually, it moves to the side. When it moves to the side in the southern hemisphere, it's going south. When it moves, that same air can also move north. You see some of this air, this warm, moist air goes this way. Some of it goes this way. If the Earth did not rotate, this is where the story would end. But the Earth does rotate, which explains night and day, and so we get a slightly different pattern. But this is the most basic level, is a pattern that happens, a kind of a spiral situation where air is rising right here, moving towards, away from the equator, and then look what happens right here. By the time the air has reached this point where it's well above the ground, it is cold and it is dry. It's lost its water. It drops down. It descends. These places where the air is dropped to are called high pressure zones. In a high pressure zone, we have high air pressure. The air is also cool and it is dry. Is it sunny out? Yes. High pressure areas do have more sun, but they have also colder temperatures at night. It's just to say that they're not as good at keeping in the energy from the sun because water and the air would act as a greenhouse gas. When the air is dry, that makes it cooler. So these high pressure zones like right here and here, where you're finding desert north and south of the equator, are because of these Hadley cells. Here at the equator, warm, moist, rising air explains that lush vegetation we have around the equator. And here, about 30 degrees north and south of the equator, are deserts with high air pressure. Now, as you're going to see in a little bit, these areas of high and low air pressure don't always stay exactly in one place, but this is a general pattern for you about how air behaves around the equator. But let's have a look at this as well. I want to explore this. This is an awesome website that I highly recommend you check out. It's called nullschool, and what it shows is an animation of the Earth. It shows animation of the climate on Earth. And what you can do actually, you can toggle with the Earth, right? Like this, you can move it around. And you can also look at different climate variables. You can look at temperature, air pressure. You can look at different gases in the atmosphere, rainfall, clouds. I'm going to show you a few of these. Let's start just by looking at some of the general patterns. The map right here is showing the pattern of temperature on the Earth's surface. The more red means the warmer, yellow is kind of like in between warm, green is really quite cold, and then blue is the coldest, or actually I should say the coldest of the cold is purple. So that's your spectrum of colors right there. In fact, it gets better than that, but because we can actually find out how hot is it. At the South Pole right now, it's about negative 53.2 degrees Celsius. Isn't that cool? Whereas if you're in, say, Hawaii, 15.1 degrees Celsius. I guess because it's kind of nighttime there. Here in Smithers, let's see where we're at. About 6.4 degrees Celsius. So this is a map of the global temperature. I'd like you just to remember a little bit about how the sun, how day and light works. Just a quick reminder that you've probably heard this before. The sun rises in the east and sets in the west. This is because the Earth is constantly rotating. The Earth rotating like this here. Imagine that you're the sun. Right now, if you're the sun, well, it's nighttime. I'm recording this video at night. If you're the sun facing the Earth, well, the Earth is lit up and Smithers is facing away from the sun. I'm not recording this video at 4 a.m., but here comes sunrise. There. The sun just, well, that's so cool. Look at that little thing just appeared, right? There's Smithers. The sun just rose in Smithers. Now, the Earth is continuing to rotate. Now the sun is going to set in the west. That's the passage of one day here in Smithers. So far, so good. I'd like you also to look at the temperature patterns. Notice the obvious, that towards the poles, it's a lot colder. In fact, what you're seeing right here, this outline right here, this kind of like blob shape on the poles, why do you think it's there? Well, if you've ever been to the Arctic or seen pictures of the Arctic, you might be aware that what you're seeing right now, at least on the ocean, is the limit of the ice pack covering the Arctic Ocean, which gets bigger and smaller as the year goes by. And here we're seeing a growing ice pack in the Southern Ocean. All right. What else? Check this out. This is something else we can learn from this map of global temperature. Notice that the interior of the continent here of Africa is much hotter. Watch this. So right now we're somewhere in, I don't know, southern Libya or something like that. 28 degrees Celsius. Versus the ocean, 23.5 degrees Celsius. Let's look at Saudi Arabia. 36 degrees Celsius in central Saudi Arabia. In the Persian, off the coast of Oman right there, 28 degrees Celsius. It's hot, but in the interior of the continent, it's hotter. This is explained by the fact that water is a very special molecule when it comes to thermal energy. Water has what's called a very high heat capacity. Think about it this way. If you were to take a cup of coffee, and a hot cup of coffee, and also take a hot cup of air, yes, I mean just like a cup of really hot air, and put each of those in a room. In all fairness, we imagine we put a little lid over the cup of air so it just doesn't just blow away. Now, if we do that, and you come back 10 minutes later, which do you think is still going to be hot? Well, of course you'll know that it's going to be the cup of coffee will still be hot, whereas the temperature of the air will probably be more or less equal compared with the air in the atmosphere around it. This is because water, being a very dense liquid, has an excellent ability to store thermal energy. Thermal energy is the energy of moving particles. Water has a high heat capacity, meaning it can store lots of it, a lot more, for example, than air. This means that, in fact, also more than many other substances like rock, water is very good at doing this. And as a result of this, the temperatures in the ocean don't fluctuate quite so much. Right here, I guess this is Mauritania or something like that, 33 degrees Celsius. The ocean off the coast of it, 22. We'll see these patterns all over the place. Temperatures fluctuate more in the interior of continents. It doesn't mean that the interior of continents is always hotter. Far from it. If you look at the interior of, say, North America during the winter, you'll see that it's a lot colder in, say, Edmonton than it is off the coast of Vancouver Island. The temperature fluctuates more in the interior of continents than on the coastline. And this has huge effects on local patterns in climate. So far we've looked at the fact that it's warmer in the tropics than in the polar regions, and this comes down to how the sunlight is distributed. And I've talked to you a little bit about Hadley cells. Okay, here's where I want to go next. I'd like you to notice that we have, let's see, we'll show it with, we'll still use this one. I'd like you to notice, I'm going to zero in a little bit and see what's going on in the North Pacific Ocean near BC. These lines show air that is moving. It's wind. It's showing wind, and it's a little bit. It's maybe not what you expect when you imagine wind. When you imagine wind, you probably just imagine all the air moving towards you in one direction, and that being the case over a huge area, like walls of wind moving in your direction. That's not really the way it works, actually. Wind actually moves more in spirals if you look at it over a really large area. This is because of what's called the Coriolis effect. And this is a tricky thing to explain. And so I'm also going to give you guys some video links at the end of this video, but I'll try my best. So, we know the Earth is always rotating. Now, we also know, however, that at the equator, air is rising and then moving away from the equator, moving towards the north, moving towards the south, forming these Hadley cells. If the Earth weren't rotating, the motion would be this. Air goes up, drops down, forms an area that is high pressure. Area will move from the high pressure zone to the low pressure zone, so it would then come back. Low pressure is made here by this thermal energy arriving here and evaporating all this water. Air goes to the north and it falls down, makes a high pressure zone. That high pressure zone pushes the air back towards a low pressure area. If the Earth were not rotating, then we would just have these giant, what are called Hadley cells, doing this constantly. Air moving up and north, or down and back south in a spiral. But that's not the way it goes. The Earth is constantly rotating. So what happens is we get, instead of air just moving like this and then back, as you would see from above, the air, in order to maintain what it's called its inertial momentum, doesn't do that. As air goes up and north, it also gets deviated, turned, or deflected to the right. Air coming back towards the equator is also, in the northern hemisphere, is also deflected back and towards the right. Imagine if you're like over here and traveling down in this direction. To do this is going towards the right. So air going north is deflecting towards the right. Air going south is also deflected towards the right. Watch this. We're making a circle. Specifically, it doesn't end up being quite a circle because there's another force at play right here. We actually get spirals, like the spirals of a snail. Where's an example? There's one off the coast as I'm doing this video. There's one off the coast of BC because they're here all the time. Here's an example of a weather, what's called a weather system. It looks like a tornado you've probably seen on the internet before, or TV or whatever. Air from the equator is moving up. The Earth is rotating, and in order for the air from the equator to maintain what's called its inertial momentum, basically to keep going with the same speed, with the same speed as it was at the equator, it has to kind of twist off towards the right. And air coming back down here, in a way, is loses its, and it keeps its inertial momentum, but does that by also twisting down towards the right. So air coming down from here is twisting to the right. Air going up here is twisting to the right. Air going in this direction is twisting here. What these twisting patterns form is a system where you get these spiral weather patterns. What we're seeing right here, I'd also like you to notice the direction that these lines are going. They're going inward. We're spiraling inwards. This is doing that. The air is moving in that direction because this is called a low pressure system here. What this map here is going to show you is the same system, just using a different variable. The variable right here is called air pressure, which is basically how, with what force does air push against a surface. Now on Earth, the air pressure is always around what's called 100 kilopascals, give or take some small amount. But that small amount, the air pressure difference, accounts for a lot of weather patterns that we see. When we have low pressure systems where there is low pressure, that is associated with moist, warm air, and when we have moist, more warm air, that is actually something that co-occurs, that happens at the same time as rainy weather. So low pressure systems actually mean rainy weather with high humidity. High pressure systems are areas of dry, cool air. High pressure systems are systems that we like. In fact, here's what we've got, because basically it's just nice weather. What I like here is we actually have a high pressure system or a high pressure cell next to a low pressure cell. Notice this. Air is spiraling out from this cell right here and spiraling into this one right here. It's high pressure here, and the air is being pushed out of here and into here. But, and this is the really key point, because of the Coriolis effect, it's not following a straight line. If the Earth was not rotating at all, it would be a really quick trip. Air getting pushed from here goes straight over there. But because the Earth is rotating, and because the Coriolis effect is always causing air in the northern hemisphere to twist towards the right as it moves, it's a much longer trip for this pressure to even out. Yes, air is always flowing from high pressure to low pressure areas, but it does it in spiral patterns. So I hope that that's kind of that seeing this example right here is kind of clarifying that for you a little bit. I did want you to get a better sense of that. The other topic, let's see, what else did I want to do? Oh yeah, this map right here covers humidity. So let's look at the same part of the world, same general area. What we see right here, I think this is humidity. Yes, it is. Good. Areas that are paler in color involve more humid air. So again, this is a low pressure system, and in a low pressure system like this is where we think of as there being like the really rotten weather. If you're right here, where I've got the mouse right there, where I've just made a little green circle, look at that. It's very humid, 95% humidity. That means the air is very moist. And the air is moving pretty fast, 39 kilometers per hour. When I looked at this weather system earlier today, and I was looking at this kind of part of the weather system near the middle, but not at the middle, I was finding air speeds of upwards of 80 kilometers per hour. That's really fast when you think about it. 80 kilometers per hour, as fast as a car going, almost highway speed. Even here, this is moving. The air is moving very fast, but paradoxically, right in the middle, look at that. In the very middle of this low pressure system is the point that the air is being sucked towards in a spiral pattern. Look at that. It's only going 4 kilometers per hour in the middle. Here is your high pressure system. In the high pressure system, we have a much lower humidity, 68% relative humidity. The air is moving outwards from it, again in an outward spiral pattern. And look at that. It's only 1 kilometer per hour. So you wouldn't want to be lost in a boat out here in the middle of the Pacific, but if you were, at least it would be nice sunny conditions right there. How does this relate to, well, other parts of weather, like rain? Well, the answer is, maybe not surprising, that where the air is humid, where the air has a higher water content, it's more likely that the condensation will happen in the air. When condensation happens in the air, what do you get? Well, you get rain. Eventually, the droplets of water get big enough that under gravity, they fall together, they clump together and they fall as rain. So let's look at the next diagram right here. And what this is showing us is kind of an overlay. Again, we see these wind patterns moving around this this low pressure cell right here, right? This is the low pressure cell. The winds are moving inwards in these beautiful spiral patterns. This here, I believe, is actually showing cloud cover. What this is actually mapping out is the weather forecast for how much rain's going to fall. So if we look right here, it's saying the next 3 hours, there'll be about 0.2 millimeters of rain falling there. How about right here? 1.9 millimeters, 1.7 millimeters. So basically, it's going to rain there. Doesn't look like it's going to be all that bad, but be some rain. Now, one thing that does happen is, hey, look at this. This is what's within, when this system right here hits the coast, there's going to be more rain. How do you know that? Well, probably from personal experience. As a general pattern, you would know that around Prince Rupert, maybe Tofino, Vancouver, if you've ever been there, it gets really rainy there. What goes on with that? Well, I'll tell you one thing. I've been watching, as I've made this video, I've been watching this low pressure system. I've come back to this website a couple times over the last few days, or a few times, and this system has been slowly working its way across the Pacific Ocean, carrying this warm, moist air with it, these clouds that can drop rain onto the Earth's surface. Well, we see out in the middle of the ocean that is it raining? Yes, it's raining a little tiny bit. What happens, however, when you get to the BC coast? Well, we all know that we live in a province of mountains, that there's a kind of a chain of mountains that runs along the coast right here. that has huge effects on the climate as well, because what happens when to this warm, moist air when it hits these mountains here is that air rises. And as it rises, the air cools. And as the air cools, all that moisture condenses. When moisture condenses inside rising clouds, that moisture falls as rain. So this closeness of the BC coast to obviously the Pacific Ocean, the coast is close to the ocean. The fact that the BC coast is so often got these weather systems coming up against it explains the high levels of precipitation, rain and snow that fall on the coast. This combination of coastline with warm, moist air, with mountains, those three things put together lead to rainy coastlines, at least when those weather systems do arrive there, which in the spring we definitely get a lot of those. I guess the last thing that does sort of pan into or lead into a little bit is this concept of the water cycle. And you've probably seen this before. The water cycle is even something you're learning about in elementary school, but it kind of bears repeating. The water cycle is a very important cycle, obviously, to life. We know we need water to drink, we need water as an energy source, we need water for our crops and for health, and so on. Lots of purposes. But another thing about water is because it has such a high heat capacity, it's also another vehicle through which energy can be transferred in the hydrosphere. If we imagine, look what's happening here on the Earth's, on the surface of the ocean. The sun's rays strike the ocean right here. That energy there is used not to warm up this part. Some of it's used to warm up the water, but some of it is just used to change the water from a liquid state to a gas state. As the water is transferred, as this moist air is transferred, in this case onto a coastline, and the air rises, it drops its precipitation to the ground, forming rainfall and weather and water systems. This also involves transfer of matter, and there's also energy flows that are happening there. When air falls when precipitation falls as snow, that's transfer of different levels of thermal energy. So I don't really want to get into the water cycle anymore. I'm not making perfect connections between it and energy, but it is something that you should have as a learning piece for your climate change. So really, I've covered what I wanted to cover. I would like you to just read through those notes. I already had a lesson on the greenhouse effect, and I'm going to actually have another lesson on the greenhouse effect, connecting it with climate change. So in summary, we've looked at conduction and convection and radiation in the atmosphere. I showed you Hadley cells, and I explained how they involve air moving from the equator to the north and to the south and causing high pressure areas. So you ought to kind of a sense of what a high pressure area is. I also explained to you, however, that those high pressure areas, that it's a bit more of a complex scenario because the Earth is rotating. This causes the Coriolis effect. So air does not move. Air moves in twisting patterns rather than in straight line patterns because of the Earth is rotating and the fact that the Earth is a ball. And then we've looked at different measures of the weather, such as temperature, precipitation, air pressure, and I showed you cloud cover on the map, the movement of air from one place to another following pressure gradients, but under the effect of the Coriolis effect is wind. And we've also looked at high and low pressure cells or systems, where a low pressure system is associated with warm, moist air and rainfall events, and high pressure system is associated with cool, dry air and clear skies. That's everything I want you to know for climate. I'm also going to include two videos at the end of this to make sure, especially that the Coriolis effect is making sense to you.